Good day and welcome back to part 5 of our discussion on substitution. In this video we are going to concentrate on substitution for definite integrals. With that in mind, let me give you the quick reminder. The second part of the fundamental theorem of calculus tells us how we can quickly and efficiently evaluate a definite integral as long as we can find an antiderivative of that function little f. And if such an antiderivative happens to be big F, we simply substitute in B, put a minus sign, substitute in A, where the big F is an antiderivative of little f. With that in mind, if we encounter a definite integral where the integrand itself is something that appears to be conducive to a substitution, we can still apply that substitution. In this case, we would note from our previous experience, we would let u be equal to g of x, and the du is equal to g prime x dx. So we want to take this integral on the left that only involves the variable x. So note, even the limits of integration here are from x equals a to x equals b. And we need to rewrite this as an integral only involving the variable u. And the integrand itself is exactly what we've been doing. It becomes f of u du. But our limits of integration also need to be in terms of u. And remember, if we know something in terms of x, and we want to get it in terms of u, we simply use our substitution. So if x is equal to a, the lower limit, u is equal to g of a. If x is equal to b for the upper limit, then u is equal to g of b. And the idea is that we now have an equivalent definite integral that's going to be simpler and easier for us to evaluate. And it's worth noting that the reason we go through the process of changing these limits of integration is really twofold. One, it allows us to have a mathematically correct statement, which is important. And secondly, this equivalent definite integral has a numeric value. So once you evaluate this definite integral, you are done. So substitutions with definite integrals do not require a substitution. But one thing I'm really going to emphasize here is that whenever we use definite integrals with substitution, we must change the limits of integration. If you have encountered this technique in a previous course and you did not change those limits of integration, I would like you to forget about how you previously approached substitution and really focus in on the process that we are going to use. The reason I use this process is it will set us up for future success. This is what I consider to be the best, most efficient way to evaluate definite integrals using a substitution. So let's look at a few examples. If we wanted to evaluate the indefinite integral where our integrand function is x cosine x squared, the thing I would like you to immediately notice, or hopefully with practice be able to notice, is we have x squared inside the cosine function, and up to a constant, its derivative appears outside. So this is what I previously referred to as being kind of a function derivative pair. And that is a very good indication that we should try a substitution. And the substitution we should try is the largest inside function we see. So du would be 2x dx. Note we have an x dx, so 1/2 du can play the role of x dx. So immediately we can put our entire integrand solely in terms of the variable u. 1/2 is a constant that pulls out front, and we're left integrating cosine of u. But just to really reiterate our point previously, these limits of integration in the original integral are for x. we're putting everything in terms of u in this new equivalent definite integral, which means our limits of integration also need to be in terms of u. So we can just simply do some quick calculations to the side. We use our substitution. So our limits of integration are x equals 0 and square root pi. And the relationship between x and u is u is equal to x squared. Our new lower limit of integration would be u equals 0 squared, which is 0. And our new upper limit of integration would be u equals the square root of pi squared, which is pi. And those limits of integration are in terms of u, and we're now in that desired form. All in terms of the variable u, and it is in fact simpler, easier for us to evaluate. An antiderivative of cosine is sine. And the fundamental theorem of calculus tells us we substitute in pi, we put a minus sign, we substitute in 0. And recall, this is certainly a scenario where I need you to take the problem one step further. Trig functions evaluated at common angles. So sine of pi is 0, sine of 0 is 0, 0 minus 0 is 0. So let's investigate this idea with one more example. And the idea is exactly the same. When we encounter an integral of this form, there's really no apparent modifications that allow us to modify the integrand so that we can use our common indefinite integral formulas. Instead, the only option we really have is to do a substitution. And when we are doing a substitution, we try to pick u to be the largest possible inside function. So in this case, I would say cosine is in the square root, making it an inside function. More importantly, outside of that, this sign that we see appearing is almost the derivative of cosine. It's only off by a minus sign. So minus du is sine x dx. So once again, approaching this integral exactly as we have done previously, we can immediately rewrite the integrand so that it only involves the variable u. There's a minus with that du we will pull out front, and then what we are integrating is 1 over the square root of u. But recall our observation from above. We must change the limits of integration. So we need to take these original limits of integration that involve x and rewrite them so that they involve u. And just doing a little bit of work to the side, we can say for that lower limit of integration, when x is equal to 0, u is equal to cosine of 0, which is 1. So our new lower limit of integration is 1. Similarly, for that upper limit of integration, and once again, we just use our substitution. U is cosine x. If we know x is pi over 3, we know the corresponding value of u. So u would be cosine of pi over 3, which is 1/2, our new upper limit of integration. And once again, with substitutions, you must change those limits of integration. If you do not, you can certainly expect to lose a few points. Now, in order to evaluate this, it's always convenient to write it in terms of powers of the variable. And in this case, note, square root of u is u to the 1/2. 1 over u to the 1/2 is u to the minus 1/2. And if we would like to account for this minus sign out front, we could simply switch our limits of integration so that we're going from 1/2 to 1, and that would allow us to absorb this minus sign. Note, you do not have to switch the limits of integration. You can have a higher number on the bottom than on the top. I only do so because it's convenient to take care of that negative. Then we anti-differentiate. Minus 1/2 plus 1 is 1/2. So we have 1 over 1/2, which is 2, u to the 1/2, from 1 to 1/2. The fundamental theorem of calculus tells us we substitute in u equals 1. Minus sign, we substitute in u equals 1/2. And as usual, I am perfectly fine with you leaving your solution in this form. Once you have fully evaluated that definite integral, you get it down to a numeric quantity. As long as it doesn't involve trig functions evaluated at common angles, you can leave it in that form. So this finishes our introduction to substitution with definite integrals, and all that remains are a few more practice examples. And once again, we're to that point where if we were meeting face-to-face in class, I'd be turning the floor over to you. And if you turn to the next page of the note handout, you'll see there's 2 more examples involving definite integrals. I would like you to take some time, maybe give yourself 8 to 10 minutes, and evaluate both of those definite integrals. Hint, use a substitution. And once you've done so, go to the next video and we'll talk about them together. So stay tuned and take care.